Happy New Year and welcome to my POPL 2021 talk on Fixpoints and automata for asynchronous hyperproperties. My name is Jens Gutsfeld and this is joint work with my colleagues Markus Müller-Olm and Christoph Ohrem. In order to give you an outline of what asynchronous hyperproperties are, I will first of all recall the notion of a classical property and then discuss the relation to hyperproperties. Recall that in model checking, we are given a system, usually some Kripke model, and we have executions of that system that we call traces. Now, a property is basically just something that I can determine by looking individually at each trace. So for example, when I want to know whether or not a given error state is reached, I can look at every trace individually and see whether that state is reached. Now, hyperproperties are a generalization of properties in which we have to look at all the traces simultaneously. For example, when we want to know whether the mean execution time of the system is bounded by some k, we have to look at all traces simultaneously, sum up their execution times, and then average it. And the same relation is true for other properties like security properties, which we will come to later. They also cannot be inferred by looking at traces individually. So, of course, hyperproperties require special kinds of formalisms to express them. And in this talk, we are interested in the temporal logic approach to model checking and the temporal logic approach to hyperproperties. And we want to discuss a new temporal logic for hyperproperties. Now, in classical model checking, we have the familiar situation that we are given a property specified by some temporal logic and a Kripke structure K, and we want to check whether the formula holds for that structure. Now, of course, common logics are logics like LTL, CTL, or the modal mu calculus, which can express familiar properties like reachability or liveness. But what all these logics have in common is that whenever they have quantifiers within them, the quantifiers are totally anonymous. So as you can see below in the formula EF-AGP, the EF part and the AGP part cannot refer to each other. So for example, the AGP part cannot refer to the quantification given by the EF part again, because there are no variables or names attached to the quantifiers. And precisely for this reason, we need new logics to deal with hyperproperties. As it turns out, there are already several temporal logics that are able to express hyperproperties, but today I have chosen to present just two of them because they motivate our own work, namely HyperLTL and HyperCTL star. And what these logics do is they take LTL and they take CTL star and they add quantification over named paths. So as you can see here, we have universal quantifiers and with names attached to them, namely pi and pi prime. And now in the innermost part of the formula, the atomic propositions can now refer to the names. And this allows us to compare and relate different paths and thereby also express a number of previously studied hyperproperties that motivate the study of hyperproperties altogether. Now, an obvious question you might ask is whether there is actually need for a new hyperlogic or whether the previous hyperlogics are sufficient. Now, what all previous hyperlogics have in common is that specifications in them are synchronous. So what does this mean? It basically just means that whenever you take a temporal operator, such as the next operator or the until operator in LTL, you will advance all paths simultaneously and lockstepwise. So if you take the next operator, all paths will be advanced by one step. You cannot, for example, say, I want to advance the first path by 3 steps, the second path by 5 steps, and the third by 9 or so. And we believe that much important interaction between paths is actually asynchronous, which becomes obvious when you look at, for example, concurrent systems which involve multi-threading. And we therefore decided to develop a new hyperlogic called HMU, which can take asynchronicity into account. So let us outline what our logic HMU consists of. So in a nutshell, we take the linear time mu calculus, which is a linear time variant of the well-known modal mu calculus, and we add quantification over named paths as in HyperLTL, and we add indexed successor operators. So formally, we have indexed atomic propositions, meaning again, atomic propositions can refer to paths. We have the well-known logical connectives not, or, and. We have path quantifiers equipped with path names as in HyperLTL. we have the indexed next operators. So every next operator is indexed by one path, which it is about to advance. And we have the well-known smallest and largest fixed point operators, which allow for more complex reasoning. Now, the best way to discuss a new specification logic is to discuss what can be specified in it, and we will start with security properties expressible in h-mu, and we will start with the observation that everything that can be specified in HyperLTL can also be specified in h-mu. So basically, just like LTL can be straightforwardly embedded into the linear time mu calculus, so HyperLTL can be straightforwardly embedded into h-mu. And as you see here, we can define classical temporal connectives like G generally and F future, both for single paths and for multiple paths at once. And given these definitions, we can now express the property of observational determinism, a very important hyperproperty, which says that if we have two executions that have the same initial low security inputs, then a user who can only see low security inputs will not be able to distinguish them. This is a very important hyperproperty, but it is already expressible in HyperLTL. So it does not by itself motivate our new logic, but we will soon see how genuine asynchronicity can be used in h-mu and how it can be used to enrich properties like these. And asynchronicity generally requires our logic, and therefore this will be a motivation for it. Now, since this talk is about asynchronous hyperproperties, we want to explore how asynchronicity is useful in applications of hyperlogics. And a very common scenario is that we are given an actual real-world system and an abstraction of that system, meaning a model, and steps on different traces of the abstraction do not correspond to the same number of steps in the underlying system. And we now here have a formula that says that there is a path pi such that all other paths pi prime will repeatedly agree with pi on some atomic proposition A, and in particular, this agreement can be obtained asynchronously, meaning a step on pi can be matched by an arbitrary number of steps on pi prime. And while this property in itself does not appear very useful, it can be made very useful when we add it to other properties, for example, the security hyperproperties we just saw, because now we can accommodate the potential mismatch of steps or numbers of steps. As I said earlier, our new logic h-mu is very useful for specifications for concurrent programs, or more precisely for hyperproperties in the context of concurrent programs. So we here have a scenario in which we have two paths, pi0 and pi1, which represent two different threads in a multi-threaded environment and synchronize via locking, where locks behave in the usual manner. And we want to express that two threads can reach an error state, which is identified by some formula, and we want everything to happen in a lock-sensitive interleaving. So how do we do that? Basically, since it's a reachability property, we use the smallest fixed point operator, and then we always check whether the error state has already been reached, or in the other case, we advance asynchronously one of the threads which can currently perform a step, and then we check again. And we believe that this type of property shows that h-mu can be used to express very elegantly properties about concurrent systems, because we can just take the natural description that you see in the sentence there and translate it very straightforwardly into an h-mu formula. So far, we have looked at h-mu as a new logic or new fixed point calculus for asynchronous hyperproperties. Now, we want to introduce our new model of AAPA, alternating asynchronous parity automata, which are a variant of alternating parity automata operating over words, but this time operating over multiple input words. So what do AAPA consist of? Basically, we have a set of states Q. As usual, we have omega as an assignment of priorities to states in Q, or parities, whatever you want to call them. Then we have a Boolean formula which describes the possible initial states, and we have formulae which describe the transitions. And of course, since we operate over multiple input words and we want to progress asynchronously, we need to describe which direction we want to take. So as you see in the last line, the formulae also have to take directions into account. I also briefly want to comment on the notion of a run of an AAPA, which is very similar again to the notion of a run of a classical alternating parity automaton over words. So We also have a tree here, but this time over n input words, and we denote for every input word by some offset counter how far we have progressed, since progress is asynchronous, and therefore this needs to be denoted for every word individually. And finally, we have the usual parity acceptance condition. So we look at every path individually in the tree, look at the smallest priority occurring infinitely often, and the path is accepting if that priority is even, and the run is accepting if all paths are accepting. And finally, the automaton accepts if there is some accepting run for the input words. So far, we have seen two approaches to asynchronous hyperproperties. The first being our new logic HMU, and the second being AAPA, our automata model. But the question is, of course, how are these two approaches related to each other? And a major point of our paper is the so-called Correspondence Theorem, which relates both formalisms. So it has two directions, and in the first direction, it says that if you have an AAPA, you can also have a quantifier-free formula psi A in HMU that describes the same set of traces. And the other direction also holds, meaning if we have an HMU formula psi, we also have a matching AAPA A psi that also describes the same set of traces. Now, in both cases, this is over fixed trace assignments, meaning in HMU we have quantifiers, but over AAPA we do not have them. So we first of all resolve the quantifiers and pick some trace assignment. And once we have done that, the formalisms coincide. So we can have for every AAPA a matching formula, and we can have for every formula a matching AAPA. So the formalisms are in a sense equivalent, which is, we think, a very useful insight and can also be useful for model checking and other purposes, as we will see soon. Now, of course, we are also interested in computational aspects of asynchronous hyperproperties, such as the emptiness problem for AAPA and the model checking problem for HMU. And both problems turn out to be highly undecidable, meaning they are not just undecidable, they are not even arithmetic. So they are at least hard for some part of the analytical hierarchy. And for AAPA and the emptiness problem, we can obtain this fact by reducing from the inclusion problem for two-tape Büchi automata. And in fact, this also presents one of the first applications of our correspondence theorem, because we can use this undecidability result for AAPA to obtain a similar undecidability result for the model checking problem of HMU. And now, what are the implications of these undecidability results? Basically, both problems are not recursively enumerable since they are not arithmetic, so we cannot have any exhaustive approximative analyses. And what this means is that we need restrictions that yield us decidability. To discuss restrictions and approximations of asynchronous hyperproperties, we first need a small technical notion, namely the notion of an extended syntax tree of a formula. And basically, this is just the regular syntax tree, which you all know. And then we iteratively replace fixed point variables by the formulae they belong to in order to obtain a possibly infinite tree. The first restriction we want to discuss is k-synchronicity. In a nutshell, k-synchronicity says that words are allowed to diverge, but never by more than some fixed index k. So for example, when k equals 2, one word is allowed to be ahead 2 steps of the other, but not 3 or even more. And if we know that some AAPA has only k-synchronous runs, we know that its emptiness problem is decidable, and indeed we can check for every AAPA whether it has a k-synchronous accepting run in exponential space. And furthermore, this result is optimal because we have a matching hardness result. And it is great to notice here that the hardness is only due to the number of input words n, but not due to the synchronicity index k, meaning if we fix the number of input words but increase the k, the synchronicity index, then the blowup is only polynomial but not exponential. And likewise, we can define this restriction for HMU formulae by looking at the extended syntax tree. We take every finite path of that tree and look at the number of occurrences of different indexed next operators and note their difference. And if that difference is bounded by some k, then the h-mu formula is syntactically k-synchronous. So we have a matching notion both for h-mu and for AAPA. Now, our notion of k-synchronicity is somewhat limited because paths are never allowed to diverge unboundedly. And this is why we will have a look at a different restriction, namely context bounds. So what is a context? Basically, a context is a subpath of one of our runs, such that during that subpath, we only look at one direction. We do not switch between directions. And we want to consider now only runs with at most k contexts on every path. And we can again ask whether an AAPA has a k context bounded run. And this is indeed decidable, albeit with much higher complexity than the matching problem for k-synchronous runs. So this time we have k-1 X-space completeness. So the problem is in general non-elementary if we do not fix the k. The notion of k-context boundedness of AAPA once again has a matching syntactic restriction in h-mu. This time we look at the extended syntax tree again, but at every path instead of just every finite path. And we say that an h-mu formula is syntactically k-context bounded if the number of switches between different indexed next operators is bounded by at most k-1. And now what is interesting to notice is that for k-context boundedness, but also for k-synchronicity, if we take the formulae with this restriction and we translate them into automata using the correspondence theorem, then we will get automata with the matching restriction, which implies that this notion is somewhat robust between h-mu and our automata. And finally, I should mention that the fragment of k-context boundedness, or the concept of context bounds, is inspired by a concept of the same name in the literature of multi-stack pushdown automata, for those of you who are familiar with that. Of course, our paper is not the last word on asynchronous hyperproperties, and many interesting questions remain for future research. And 3 of these questions I would like to briefly outline here. So the first is the extension of h-mu by arbitrary quantification. Recall that h-mu is a linear time logic because we allow quantifiers only in the front, but not in arbitrary positions as in CTL star or hyper CTL star. And we would like to make that happen by extending our approaches to allow quantifiers in arbitrary positions and adjust our results accordingly to have a more general logic. The second problem we would like to study is the identification of further restrictions of both AAPA and h-mu. So the reason for that is that the restrictions we saw today, while very natural, are still somewhat limiting. And possibly there are further restrictions which might be somewhat more involved and possibly also might not have very simple syntactic characterizations in h-mu, but which still might be very useful for practical reasons. And it would be very interesting to find these types of restrictions and study them. And finally, we would like to compare our logic to existing hyperlogics, namely to MSO with an equal level predicate. So recall MSO is the logic, monadic second order logic. So we have quantification over sets, we have quantification over individual members, we have the usual logical operators, and we now also have an equal level predicate. So we have our tree, and we can ask for 2 nodes in the tree whether they are at the same level. And with this predicate, MSO becomes able to express hyperproperties. And while we have outlined an embedding of h-mu into MSOE, only informally, but we have somewhat outlined it, we do not know yet the precise relation of these 2 logics. So whether they are possibly equivalent or whether there is some other interesting connection yet to be found. And finally, we would also like to compare our work to hyperlogics with team semantics. Team semantics is a very new approach to semantics and has also been studied for hyperlogics. And we would like to see, first of all, how the logics compare to ours in expressive power, and also how the team semantics approach could possibly be used to enrich our own approaches. Finally, as we are approaching the end of this talk, it is convenient to once again summarize what we discussed today. So first of all, we introduced the concept of asynchronous hyperproperties, and then introduced the first systematic fixed point calculus for hyperproperties. Secondly, we introduced AAPA as an automata model for asynchronous hyperproperties, and we unfortunately showed the most interesting problems for both models to be highly undecidable. But fortunately, we could also find possible restrictions that allow us to obtain decidability once again. Now, of course, the paper is much more detailed than this talk. And in the paper, you will additionally find detailed analyses of both the model checking and the satisfiability problems. So the satisfiability problem is of course, to decide for a given logic such as h mu, whether a formula has a set of traces fulfilling it. So whether we can indeed find such a set at all. And we also tackled that problem, and we also found very precise results for that problem. And finally, the correspondence theorem is described and proven very explicitly in our paper, and you will find effective constructions of the translations of formulae into automata and vice versa. Now, having that said, I thank you all for your attention and for your interest in our paper. And me and my colleagues are very much interested in answering any questions you might have, and also in discussing asynchronous hyperproperties with you.